Okay, we talked previously in general about different reactions that can be used to synthesize alkyl halides. And some of those reactions we looked at were very familiar, like the acid plus the alkene. That's our bread and butter reaction. But some of the reactions were unfamiliar to us. And in this video, we're going to talk about the addition of a halide, X2, whether that's chlorine or bromine, to an alkene. Now, if we were to guess about this mechanism, it would maybe look a lot like this acid to an alkene, but there's some important differences. And so let's try to see what might happen in the reaction of these two things. So let's have a halogen here, Br2. We're going to react it with an asymmetrical alkene, and immediately we've got a problem. Right? We can identify a good nucleophile here. The extra electrons in this double bond might be nucleophilic, just like they were when we reacted with an acid. However, we have a real nonpolar bond here. We don't have an obvious positive charge anywhere in this molecule that would react with this nucleophile in the alkene. Now, it does react, and we sort of cheat here and imagine that the polar bond isn't completely polar, and at one instant in time, one of these bromines might have a lion's share of the electrons, and the other one might have a lower electron density. And so we can label one of these bromines, doesn't matter which one, with a delta positive, partial positive charge, and the other one with a delta negative. Now, you wouldn't predict this just based on theory, but it does happen, and there's been experimental evidence to show that this reaction takes place. And so now that we've labeled one of these bromines with a partial positive charge, the first error of this reaction is pretty obvious. The nucleophile with the electrophile. This bromine has too many bonds, so this bond will break. The other bromine would be happy to take those electrons to generate our bromide anion. And if we were to guess based on previous knowledge, we would think that one of these carbons has a new carbon-bromine bond. But this is where this reaction is a little different. We don't generate a straight carbocation intermediate like we did with this reaction. In fact, these two carbons don't really choose which one of them is the winner, which one of them gains the new bond with the bromine, at least not immediately. So the intermediate that forms is something new, and it is called a bromonium intermediate. Neither one of these carbons has formed a complete bond with the bromine. Both of the carbons are sharing that bromine with a partial bond. This bromonium intermediate has a positive charge, and that positive charge is shared around this ring, three-membered ring. This is our bromonium intermediate, bromonium. And if we had chlorine in the reaction, it would be a chloronium intermediate. This is weird, it's strange, but there's experimental evidence to show that it exists. And the existence of this intermediate actually predicts a certain type of product selectivity that we see when we do these experiments for real. Now, once we've written out this bromonium intermediate, the next step of the reaction is pretty straightforward. This negative charge on the bromide is going to react with the positive charge of the bromonium, and we're going to get an attack of this nucleophile, and it can attack either one of the carbons in the bromonium. Here I'll have it attack more highly substituted carbon because the positive charge is going to spend a little more time on that more highly substituted carbon because we know tertiary carbocations are more stable than secondary. Now, if we form a new bond between this bromine and this carbon, this partial bond will break and it will result in the formation of our dihalide. first bromine is attached to that carbon. Our second bromine came in with this set of arrows at the more highly substituted carbons, and we end up with our dihalide. Now, something important about this mechanism that sometimes has consequences on the product is really how these arrows occur as the bromide is attacking the bromonium. This bromonium structure is on one side of the molecule, and it really blocks the second bromine from attacking on that same side. If you notice here, I wrote the second arrow on the opposite side of the first bromine, and that shows what we call an anti-addition. An anti-addition is when the two things being added to the double bond are added to opposite sides of the molecule. And this is the case in this electrophilic addition because the bromonium intermediate blocks an attack by the second atom on the same side. Now, for this product, it doesn't really matter whether one bromine attacked on one side or the other. Since we just have a single bond in the middle, we have free rotation, and so there's no cis and no trans. That anti-addition isn't locked in place in the molecule, and so there's really no consequences. And so can you think of an alkene where there would be consequences to this anti-addition? Well, we've seen it before, right? What type of molecule is free rotation of a single bond restricted in? Well, here's an example. A ring. If we do a bromination of an alkene in a ring, a bromonium intermediate is formed, an anti-addition occurs, and the correct product or major product from this addition would be when the two bromines are on opposite sides of the ring. This reflects the anti-addition, and since this molecule is in a ring, we can't just freely rotate that single bond to get these bromines on the same side. Okay, let's look at maybe a more clear version of this mechanism. Here we have a bromine attacking this double bond. This pH stands for a phenyl ring. A phenyl ring is just a benzene ring. So it's something big and bulky over here. Again, we have the double bond attacking a bromine, this bond breaking to form our bromide, our bromonium intermediate, the bromide attacking in an anti-fashion to the opposite side of the bromonium. Here this shows it attacking this carbon or this carbon. Both of these are equally substituted, unlike my example where this was the more highly substituted and probably is favorable. In this case, probably this attack is more favorable because there's less steric hindrance. There's a big bulky phenyl group over here that might get in the way of a bromide attacking here. Again, the bromide attacks, the bond breaks, the bromonium breaks apart, and we get a dihalide. Okay. Now let's show a little video of this bromonium forming. Here it is. Okay. Let's see if we can go back to the beginning. Right. Here we have our alkene and a bromine. The electrons from this double bond are going to form a bond with one of the bromines and share it in the bromonium intermediate. So let's look at that happening. There we go. We've got our bromonium intermediate, which is a positively charged intermediate. Our bromide nucleophile is formed, and this bromide in the second step of the reaction will have to attack from the opposite side than the first bromine. This way is restricted. It's blocked by the bromonium intermediate, so it's going to have to come on the opposite side. And in this case, this second bromide would probably attack this more highly substituted carbon over here.